Hello and welcome to Chemistry with Dr. Clark. In this video, I would like to talk about heterogeneous equilibrium expressions and specifically about calculating the value for the equilibrium constant. Now, if you're feeling very comfortable with writing equilibrium expressions for heterogeneous equilibria, then you're in the right place. I do have a related video. It does talk about how do you do the heterogeneous equilibrium expressions without the calculations. So if you find that you're getting a little bit lost when I write the expressions, then you may want to pause the video, go back to the one that speaks specifically about writing expressions, and then come back and do the one that talks about the calculations. Okay, I do have the link in the description below. Okay, so if we do just a quick review, if you're talking about an equilibrium, equilibriums are reactants that turn into products, and the products then turn back into reactants. So what I've got here is a general version. It has the capital letters, which represent the chemicals, and it has the lowercase letters, which represent the numbers used to balance the equation. So if I put an example in here, let's say that we have H2 gas reacting with some Br2 liquid in equilibrium with 2 HBr gas. Okay, so the reactants, capital A and capital B, would be the H2 and the Br2. Instead of having two products, I only have one. So the capital C would be like my HBr. And the lowercase letters would represent the numbers used to balance it. So it'd be like a 1 and a 1 and a 2. Now, if I want to write an equilibrium expression for this, okay, this entire thing here is the equilibrium expression. Okay, it's basically the concentration of the products divided by the concentration of the reactants, and they have powers that used to be the numbers that balance the equation. Okay, so these lowercase letters here are the stoichiometric coefficients, the numbers used to balance, and in the expression, they become powers. Okay, so if I do that for this, KEQ, products on the top, reactants on the bottom. So I have only one product. It will be the HBr. Now, I could know a lot of things about HBr. I could know its moles, or its density, or its mass, or its volume. I could know a lot of things. But for these calculations, what we really like is concentration. And in order to tell everybody that it's going to be concentration, we use square brackets. So I'm going to put some square brackets around this to show concentration. Now, let's talk about our powers. Originally, I used the 2 here to balance this equation. Because there's a 2 used to balance the HBr, the power for HBr is going to be a 2. So it's going to be the concentration of HBr squared. Now I'm going to put my reactants in the denominator. So my first reactant is an H2. So H2, we're going to use the square brackets to show concentration. And because I used a 1 to balance the equation, this is going to be to the power of 1. Now, normally, if I have a second reactant, I would put my second reactant here, put square brackets around it, and raise it to its power. But in a heterogeneous equilibrium, you have the chance of having reactants and products that are liquids or solids. And in the video that talked about heterogeneous equilibrium expressions, just the expressions, I did discuss why we leave them out. So if you have a solid or a liquid in your equilibrium, you are going to omit it. So solids, liquids, leave them out. So because this is a liquid, we are going to leave it out of my expression. Okay? So what I have is this. This would be my equilibrium expression for this equilibrium. Okay? The whole thing is the equilibrium expression. The K that's out in front, this, is referred to the equilibrium constant. That's what we call that. Now, depending on what course you're taking and what worksheet you're working on, it may not be a KEQ. Sometimes for equilibrium constants, we just call them Ks, and sometimes we call them KC. the C refers to the fact that this is all about concentration, right? It's all about concentrations, so KCC for concentration. So whichever one that you're currently using in your worksheets or your course or whatever you're working on, that's the one you should stick with, okay? Because there's a couple of variations. And for these heterogeneous equilibriums, heterogeneous because you can have a mixture of solids, liquids, gases, and aqueous. Gases and aqueous, we love those. So when I write the expression, see how this was a gas and I included it? See how this was a gas, I included that? Gases are good. We love gases, we love aqueous. But if you have a solid or a liquid, we leave those out because technically they're already built into the KEQ. Okay, so let's say that we move on and do some actual calculations. So for this problem here, it says, calculate the value of the equilibrium constant. So I want to know what KEQ is equal to for the following equilibria. So I've got one equilibrium here, and then the next page has another one. So in this equilibrium, I have zinc oxide solid that's going to react with carbon monoxide gas, and it's going to form zinc solid and carbon dioxide gas. The reactants will turn into products, the products turn back into reactants, and it just kind of flows. Now, for this one here, I have given you some concentrations. I've told you the concentration of zinc oxide, 875 moles per liter. Told you the concentration of carbon monoxide, 22.3 moles per liter. So I have given you the concentration of everything. Now, for an equilibrium problem, the very first step is always write the equilibrium expression. Write KEQ equals products over reactants. Okay, if you're doing an equilibrium calculation of any sort, and there's a lot of varieties, your very first step will always be write the expression. KEQ, products over reactants. So let's do that. So I'm going to say KEQ equals products over reactants. Now, it's going to be very easy to forget that solids and liquids are not included. So for me, if I'm going to start this problem, the very first thing that I'm going to do is make a bit of a reminder to myself not to put in the solids or the liquids. So what I'm going to do is just underline this as a solid to remind myself, please ignore that, omit it. This is also a solid. So again, please ignore it or omit it. So that way when I'm writing products over reactants, I don't accidentally put in something that I'm not allowed to. Okay, so if I look at my products, not allowed to talk about the zinc. Zinc is gone. But you do have carbon dioxide gas, and we like gases. So my product is going to be a CO2. I am going to put square brackets around it because it's concentration. And when I balance this thing, there is only one carbon dioxide. So you can put a power of 1 here, or you can leave it out. It's up to you, right? Put it in, don't put it in. But that's going to be the only product we include because solids are not allowed. Now, if we look at our denominator. Denominator is about reactants. The first reactant is a solid, not allowed to include it. My second reactant is a gas. Gases are okay. So my second reactant is a CO. Put square brackets around it to show that it's a concentration. And again, there's no number in front of it, so the number is a 1, which means this is power of 1. This is my equilibrium expression. If I want to find the value of the equilibrium constant, if I want to know what this is equal to, then all I have to do is take the numbers, substitute them in, and work it out. It becomes just a math problem. Now, what I've done here is I've attempted to make you doubt yourself. And whoever's giving you these problems, they're most likely going to make you try and doubt yourself too. Because what did I do? I gave you the concentration of zinc oxide. But do you have a place to put it in your equation? No, because you left out zinc oxide because it's a solid. Right? But I gave it here just to make you question yourself, just so that you think, oh, should I have included that? Because he gave me a number for it. But you're not, right? That is meant to just cause you to doubt yourself, right? Because you know that zinc oxides are solid, so they're left out. So you do not need that number. It's given, but it's not needed. Same thing with the zinc concentration here. Zinc does not appear in my expression because zinc is a solid. I gave it to you so that you would doubt leaving it out, but that's the only reason why I gave it to you. Okay, so for these, you have to watch out for that. Sometimes the problem will just leave them out, but sometimes the problem will put it in, and you have to reassure yourself, no, solids and liquids are not part of the equilibrium. All right, so if we put our numbers in, concentration of carbon dioxide, 32.5 to the power of 1. The concentration of carbon monoxide, 22.3, also to the power of 1. So if we pull out our calculator. Now remember, power of 1 doesn't do anything, so it's like it's not even there. So this is going to be 32.5 divided by 22.3 gives me an answer of 1.46. And that's your equilibrium constant, right? This is your equilibrium expression. It's the equation used to calculate the equilibrium constant. But when the problem says, please find the value of the equilibrium constant, they want a number. And what I should have mentioned perhaps on the first page, because I do have a little note here, your K's generally don't have units. So when I find the value of K, generally I don't put a unit in. And the reason for that is because depending on what the powers are, the units are going to be different for every single equilibrium. For this one right here, right, this is concentration. So this should have been moles per liter. The carbon monoxide, see the 22.3? That should have also been moles per liter. And if you have exactly the same thing in numerator and denominator, then they cancel out and you truly are no units. But let's say that this was squared on the top. This would be squared and then they wouldn't cancel out. Right? For these problems here, the units tend to be different depending on what the powers are. And so because it's not consistent, because it'll be different for every single equilibrium, we do tend to leave them out. So the KEQ or the K or the KC, whatever you're calling it, would just be the 1.46. All right, let's try another one. Okay, so I have an equilibrium that talks about xenon gas reacting with some fluorine gas, turning into xenon hexafluoride, which is a solid. Now, first step is always write KEQ equals products over reactants. So KEQ is products over reactants. Now, before I even start, I got to remind myself, liquids and solids don't count. So if I look through this, I do have a solid, which I am going to leave out. Gone. All right, so now let's write our expression. You always put your products in the top, in the numerator. So if I look here, I had only one product, and I'm not allowed to use it. So I have nothing to put in the numerator. If you have nothing to put in the numerator, you just put in a 1. Right? Because if I look back here, if I had multiplied this by 1 and this by 1, does that really change my calculation? No. Right? Really, there's a 1 multiplied by the numerator and there's a 1 multiplied by the denominator, but we don't write them because they don't really change anything. The only time you have to worry about it is when you have nothing else there, right? I have no product that's allowed to be written in the expression. So I'm going to put in just the 1. Now, if we talk about our reactants, first reactant is xenon, square brackets to show concentration. There's one of them, so that's power of 1. I'm just going to leave out the 1. The second reactant is fluorine. Put some square brackets around it to show concentration. And when I balanced it, there was a 3 in front, so this is going to be power of 3. And if you have more than one reactant or more than one product, there's a multiplication between them, right? Even though there's an add in the reaction, there is a multiplication in the equilibrium expression. Now, I did the same thing here that I did the last time, right? See how the xenon hexafluoride was a solid, and I'm not allowed to include it. I still gave you a concentration for it, right? Which you don't need. and it's only meant to make you doubt yourself. Okay, that's a big part of these questions. Okay, now it's just a math problem. Take the numbers, substitute them in. So KEQ would be 1 over concentration of xenon, 0.25. Concentration of fluorine, 0.35. And don't forget to cube it. That's probably the most common mistake. Most people will write this, the equilibrium expression, correctly. And then when they're substituting the numbers in, they're so focused on putting the numbers in that they forget to write down the powers. Right? So this is a power of 3. Don't forget to keep your power of 3. Now, let's talk about doing this with your calculator. If I put this in my calculator exactly as it's written, my calculator will not give me the right answer. Okay, if I say 1 divided by 0.25, times 0.35 to the power of 3, that's not the right answer. Because what my calculator thinks that I'm doing is dividing 1 by the 0.25, but then it believes the 0.35 is off to the side. It doesn't understand that the 0.35 is also part of the denominator. So you're going to have to do one of two things. You're going to have to use brackets when you put it in your calculator. That's a possibility, right? So what I should have done was say 1 divided by, open bracket, 0.25 times 0.35 to the power of 3, close bracket, equals, right? That's the right answer. Now, if you are not really happy about using brackets, there is a way around it. This 1 is divided by the 0.25, but this 1 is also divided by the 0.35, right? They're both in the denominator, so the 1 is divided by both of them. Okay, so when I use my brackets, I got an answer of 93.3. What I could do is just do it as two separate divisions. I could say 1 divided by 0.25, okay, that's my first division, divided by 0.35 to the power of 3, right? Divide by the first one, divide by the second one. And it still gives me 93.3, same answer. These problems here, because you have a lot of stuff in your denominator, it's very easy for your calculator not to understand that it's all in the denominator. So you're going to have to practice these problems a few times to make sure that your calculator skills are giving you the right answer. So my suggestion is that when you finish the video, go back, pause it when I get to here, do the calculation yourself, and then check to see if the answer is right. Make sure that you can make your calculator give you the right answer. Now, if we do talk units, right, this has different units. In the last one, you had a concentration over a concentration, moles per liter over moles per liter, and they just canceled. If I talk about the concentration units here, there's no units in the numerator because there's no concentration. What do you got in the bottom? I've got moles per liter. That would be the concentration for the xenon. And I've got moles per liter cubed, right? Because that's concentration of the fluorine cubed. So if you're talking math terms, this is like saying 1 over x times x to the 3. And if you are multiplying two things with the same base, you can add the powers, right? So this would really be 1 over x to the 4, which would be 1 over moles per liter to the 4. Every single equilibrium, if you actually include the units, would give you units for the equilibrium constant, but they'd all be different, which is why we tend to completely ignore it. Because if it's different in every single situation, right, there's no consistency, so we just tend to ignore it. All right, let's try one more. So for the last one, I have barium nitrate aqueous, good. Sodium hydroxide aqueous, good. Sodium nitrate aqueous, good. And barium hydroxide solid, not so good, right? We don't like solids, we don't like liquids. First step in any calculation involving an equilibrium is the equilibrium expression, right? This thing. Products over reactants. Well, between the two products, there's only one of them that I'm allowed to use. So that'll be NaNO3. Square brackets to show concentration. Power of 2, because the 2 was used to balance it. In the denominator is your reactants, and both of the reactants are allowed. So this would be a BaNO3 twice. Okay, that's a long chemical, but that's its name. Put square brackets around it to show concentration. You use the 1 to balance it, so it's a power of 1. Second reactant, sodium hydroxide. Square brackets to show concentration. To balance the equation, I did have a 2 in front of it, so let's put a 2 here. And because we have 2 reactants, we'll times them together. Okay, so I've included these 3 because they're all aqueous. Aqueuses are acceptable. I've left out the barium hydroxide because it is a solid and we don't do solids. And for the third time, I have attempted to make you question yourself because I've included a concentration for barium hydroxide. If the barium hydroxide is not in your expression, then you don't need the concentration. But I did give it to you just to make you doubt yourself, right? Okay, so if we substitute in our numbers, what is the concentration of sodium nitrate? Sodium nitrate has a concentration of 0.2000, and it's squared. Don't forget to use your powers. In the denominator, I have a barium nitrate. So if I look through, concentration of barium nitrate is 0.0707. It has a power of 1, so power of 1. And the last chemical is sodium hydroxide. Sodium hydroxide is also 0.0707, but this was squared, so this will be squared. Okay, don't forget to bring your powers down. And now it just becomes a calculator problem. So I'm going to do the double division thing. I'm going to put this in, divide it by this, and then divide by this. So 0.2000 squared divided by 0.0707. So I've divided by the first one. Divide by 0.0707 squared equals. And that gives me an answer 113. Now, there are units because there's moles per liter in all of these, but because it'll be different from the first 2 we did, for KEQs, we tend to ignore it. So I'd call this answer 113, and that would be my equilibrium expression. Okay, so for these here, the biggest thing to remember is that your solids and your liquids, leave them out. We don't like solids or liquids. If you got a gas, gases are okay. If you got an aqueous, aqueuses are okay. But you got to leave out the solids and the liquids. And when you write out your expression and then you substitute in, don't leave out your powers, right? That's one mistake that we see often. So again, I'd like to thank you for joining me here at Chemistry with Dr. Clark.